This topic is on vector. So for some of you, I think most of you probably, big part of this is revisions. So you probably have come across some of this, and maybe there are a few new things here that probably you will encounter as well. Okay, so before I go into this, I have registered I registered all of you onto my Moodle, but I'm not. If I missed anyone, please do let me know. But I believe I have enrolled everyone, and my lecture slides will be on Moodle. Okay, so if you want to take notes, you may do so as well. Okay, so the learning outcome of these topics. So first we're going to look at vector algebra, and then briefly talk about coordinate systems, and then gradient of a scalar field, divergent theorems, curl of a vector field, and then two nonce identity. So stock theorems, I'll leave it to another topics, so I'm not going to cover it here. So these are the things that related to these topics on vector. Okay, so I'm sure you know what is a scalar and what's a vector. Okay, scalar is some things that has no direction. So things like length, area, temperature, pressure, and voltage. These are the things that we call a scalar. So it doesn't matter which direction you point, it has the same value. So scalar can be, most of the time is positive, but sometimes can be negative as well. For example, your voltage, it can be a positive voltage or a negative voltage, because voltage is a potential, is between, depending on where you put the reference. Okay, so that is scalar. Vector is something different. So vector depends on the direction as well. Okay, so if I have a magnitude and a direction, something that has the same magnitudes but different direction, they are different things. Okay, so if I have a force, so let's say if I have a box here, I put the force here, putting a force here is two different things. Okay, so that is a vector. Or if I put the force at an angle here, it's different, although they have the same magnitude, but because we apply it at the different directions, then that has a different effect on that box. Okay, so that is a vector. So vector, that's what we're going to look at in these topics. A directed line segment is called vector. Its length is called the length of the vector. The direction is called the direction of the vector. The length of the vector is called the magnitude of the vector. So normally we draw a line and then we associate the length of the line with the magnitude of the vector. And then we use either a boldface to represent a vector, but in writing it's difficult. I mean, on paper, if you write, you can write a boldface. So we normally use either arrow on the top, okay, or you also use a curly at the bottom as well, okay, to represent vector. But on type materials, we can use boldface to represent vector as well. Okay, so here is that two vectors are only equal if they have the same magnitude and same direction. So even though if they have same magnitudes but different directions, they are not equal. Okay, so that is vector. So a very brief run through what vector is. Coordinate systems. I'm sure you're very familiar with two-dimensional coordinate systems, but in this module we might use three dimension coordinate systems because we want to solve problem in free space. Okay, so for example, here is a three-dimensional Cartesian coordinate, so you had x, y, and z. So in vector calculus, if you want to solve the volume inside this, we define, let's say, a small cube. We have said that this side here is dy, and this is dx, and then the height is dz. So if we want to work out the volume, we integrate this, do a volume integration of dv, and dv is the volume of these small tiny things, and therefore we integrate it dx, dy, dz, and then depending on the limits, how big that volume we're trying to solve. So if, for example, I want to solve the volume of this thing here, and then you have the limits from 0 to 1, 0 to 1, 0 to 1, and then you work out the volume of that cube there. Okay, so there are other coordinate systems as well. I'm not sure whether you have learned them. We have cylindrical coordinate systems, and then we have spherical coordinate systems. So you can actually convert from one to the other. I'm not going to go into details of that at this point, but when we need them, I will probably run through it again as a revisions of different coordinate systems. Instead of dx, dy, dz, then you probably have dr, d delta, d phi, and things like that. Okay, so. But at this point here, this is just brief introduction into coordinates, so we're just going to look at Cartesian here of x, y, and z. So in coordinate systems of this, so every point in space, we can write down a point here, x, y, and z. Okay, so in terms of vector, that will be a vector pointing from the origins to that particular points x, y, and z. Okay, so similarly you learn in two-dimensional. Any points here, x, y, you probably learn this. This will be a vector of x of I plus y of j. Do you learn that? Okay, so you can either write your vector in this form, or you can write the vector as x, y, or some use x, y. So many different ways of representing your vector. Okay, and I and j is called the unit vector, which I'm going to talk about that later on as well. Okay, so a vector PQ indicates that the vector initiate at a point P and terminate at point Q, where P and Q are coordinates within my three-dimensional coordinate space. Okay, so if my P is x1, y1, z1, and my Q is x2, y2, z2, then I can work out my vector A, or my vector PQ, pointing from P to Q. Okay, so this here indicate that we start from P pointing to Q. And this point here is a space, a vector space in my three-dimensional coordinate systems. Sorry, 1. And this will be x2, y2, z2. And then we can work out our vector A. So my A1 here will be the difference of my A2 and A1. Sorry, my x2 and x1. Okay? And my A2 will be the difference of my y2 and y1, and so forth. Okay? So this gives me my vector. So in my if I draw a three-dimensional, so this could be my PQ vector. So if I move this vector, okay, to the origin, this vector will be something like that. So instead of pointing from P, I make P to go to the origin, and this will be the coordinate A1, A2, A3. Okay, so it is the same vector because it has the same magnitudes and pointing at the same direction. Although they originated from different point, so my PQ vector originated from P, this vector here originated from the origin, but they have the same magnitudes pointing in the same direction, so they are the same vector. Okay? To work out the magnitudes of that vector, and that is simply your Pythagoras theorem. Okay, so you take A1 squared plus A2 squared plus A3 squared and then square root of the whole thing. And that gives you the magnitudes of that vector A. Okay, any questions up to here? I think it's still quite revision stuff. Unit vector. Okay, so unit vector we use, I think in maths you use I, J, and K. Okay, so that implies that I is a unit of my x-axis, J is a unit in my y-axis, and K is a unit in my z-axis. So normally we associate a unit vector with a value of unity, 1. Okay, so my unit vector here has a value of 1. So A1 has a magnitude, so times 1 is still going to give me A1. Okay, so I have 1.3 times a unit vector which has a magnitude of 1. So the whole thing is still going to give me a magnitude of 1.3. So anything times the unit vector will be itself. Okay, because the unit vector has a magnitude of 1. So in this case here, my A1, A2, A3 vector can also be written as A1 times I plus A2 times J plus A3 times K. And this is another way of writing vector. Okay, so the other things to take note is that my I, J, and K are orthogonal, meaning that they are 90 degrees from each other. Okay? So this is how we represent that in maths. In engineering, very often, instead of using I, we use the unit vector symbol for the unit symbol for the x-axis. So instead of I, we write A with a, I don't know, something not right. Okay, so we write A. Okay, we write A with a caret on the top and then X subscript, and then we write here, we write A with a Y, and then this is a Z. Okay, so that is how we write them in engineering. So A with a caret on the top, and then subscript X, Y, and Z. Okay, and that is what we're going to adopt in this module instead of I, J, and K going forward. Okay. Another terminology that used in vector is called vector space. So in this module, we only deal with a vector space in a three-dimensional. So our vector space is always something not right. Let me. Okay. So so with vector space is denoted by the letter R, and then the superscript of that tells you the dimension of the vector space. I think in this module, I just put it here just to complete the vector topics, but it's not really so important. Everything we deal with here is most likely to be three-dimensional, so it will be three-dimensional space using a three-dimensional coordinate system. Okay. In vector space, there can be n number of dimensions, so we can have r to the n, means that our vector will have a1, a2, all the way to an. Okay, so more than three, we can't actually visualize in free space, but mathematically we can use more than three-dimensional in mathematics. We can use the fourth dimension for something else. So for example, in calculation, we have a free space, three-dimensional. We can use the fourth dimensions. Let's say we wanted to record a temperature, or we want to record the pressure, things like that. So you can increase the dimensions of your vector to account for something else, but not something you can visualize in 3D space. Okay, so mathematically possible, but in free space, it cannot be visualized more than three-dimensional. Okay, so next is products of vector. Okay, so product of vector field. The first one we're going to look at is called dot products or a scalar product. So we have two vectors here, vector A and then vector B, and between them there's an angle theta. Okay, so vector A has a magnitude, vector B has its own magnitude, and these two vectors pointing at two different directions. Okay, so dot products, we write them as A with a dot, B, and mathematically that is equals to the magnitudes of vector A times the magnitudes of vector B, and then times cosine theta. So what this product does is actually to measure how aligned the two vectors is. Okay, so if my A and B are aligned, which means that theta is equals to 0, okay, then cosine theta will be equals to 1. Okay, 1. So that will be equals to the multiplication of the two magnitudes of the vector. Okay, which means that that's the maximum you can get out of this product. If A and B are orthogonal, meaning that they are 90 degrees apart, what is cosine theta? Is 0. Okay, which means that these two vectors are not aligned at all. Okay, so it has the dot product equals to 0, which means that they are orthogonal to each other. They are not aligned. They are 90 degrees between them. Okay, so in a way, this measured how aligned the two vectors is. The other one is a cross product. The cross product is written as A with a cross B. Okay, and what you end up with a cross product vector, you end up with another vector. Okay, so just now a dot product, I got two vector dot product, I end up with, this is a scalar, it doesn't have directions. Okay, so it's just a magnitude. A cross product, what you end up with is another vector. And to work out the direction of this vector, so if I have A cross B, then you can work out the direction using what we call the right hand rules. Okay, you use your hand, you can work out the direction of the product of that vector. So your hand, okay, your pointing finger is the first vector, and then you cross to the next vector. Okay, so your middle finger will be the other vector. So cross product A cross to B, and your thumb gives you the direction of the third vector. Okay, so A cross B, so A first, cross to B, and then this gives you a direction of the vector. Okay, so that is if you want to work out the direction of the vector intuitively. And the magnitude of that vector is given by the magnitude of A times the magnitude of B, and then times sine theta, and theta is the angle between the two vectors. So in another, so previous one we measured how aligned they are, and this we measured how orthogonal they are. Okay, so if the two vector is 90-degree orthogonal, then the magnitude of this will be equals to A times B. The magnitude of the vector A times the magnitude of vector B, because sine of 90 is equals to 1. If they are aligned, then this vector product will give you 0, because sine 0 is 0. Okay, so this is to measure how orthogonal the two vector is, or the two vector are. Mathematically, the cross product can be written as a determinant. So the determinants, we have the first row as the unit vector of the two vector, and then the second row is the magnitude of the first vector, and then the third row is the magnitude of the second vector of the cross product. Okay, so this from here, and this is the magnitude of the vector B, and the two vector has to be of the same vector space. Okay, I mean, if you have A, or at least of the same vector space. Okay, so if there are more than that, sometimes we have, let's say, A vector is simply equals to, let's say, 3AZ. So what this means is that this is still 3 vector space of 3. Simply means that it is 0 at AX and 0 at AY. Okay, so basically, if the vector has unequal vector space, we just assign 0 to those that are not in there. Okay, and then this vector here, or this determinants, we use whichever vector has the higher order of vector space.